Okay, so here we got a T-beam, double T-beam, taking 3 plates, and we are welding them together as shown. We're told that how much stress the the weld can hold. So right across there. And we want to figure out what the maximum shear is that can be applied, maximum shear load that can be applied to the beam without breaking that weld. So, and this is one of the key instances where you're gonna, really be worried about the shear stress that's arising, and not necessarily the bending stress, because again, this is where your shear is causing the tendency for these things to try to slip relative to one another, whereas here the bending moments, obviously the bulk of that would be held by just that top bar there here, and then some of that down here as well. But anyways, the bulk of the load would be there. The highest stress would be down here. Anyways, that's not what this question is asking about. We're asking about the shear stress. So first things first, let's go ahead and calculate our I values here. So we need to find the A prime, the Y bar prime, and the I prime for each subcomponent. So get the green one, and we've got the horizontal red one. So let's start. Let's first off define our Y bar as being measured relative to this axis here. So we'll put our axes system here. So we got Z. Actually, now that I think about it, Z's going in that direction, Y is going in that direction. But so for the red, the area there got 20 millimeters times, what do we have? What is the length of that? Let me just add the 50 plus another 50 plus 75 plus 40. That's 215. From there to there. Okay. I'll do that right. I'll put that down here. 215 millimeters. It's from there to there. So 215 millimeters times 20 millimeters, 4,300 millimeters squared. And then its Y-bar location measured from the bottom there, that is going to be 160 millimeters. And then its I prime, so like its individual I component, that is 20 millimeters to the third times 215 millimeters divided by 12. So what have we got here? Okay. And then the green section here. So here I'm just gonna I'll do it for one of these, and then when we're adding it up, obviously we just multiply that by 2. So for one of these, the area is 150 millimeters times 20 millimeters. I don't know why I busted out my calculator for that, because that is 3,000 millimeters squared. Its Y bar is half of the its height, so 75 millimeters. And then its eye components are 150 millimeters to the third times 20 millimeters divided by 12. So that gives us 5625000 millimeters. Oh, millimeters to the fourth. I put my bad. I'd forgotten the fourth when I was putting the previous one on. So now we need to find where the centroid of this thing is. So I'm gonna, again, that'll be relative to the bottom. So that'll be, again, that's the sum of our A prime Y prime Y bar prime divided by the sum of the areas for each of those segments. So 4,300 millimeters times 4,300 millimeters squared times 60 millimeters plus 3,000 millimeters times 75 millimeters. And you got to remember there's two of those, so multiply that by 2. And then all that divided by, what's the total area there? 4,300 plus 6,000. 10,300 millimeters squared. So let's see here. So that gives us a Y bar location of 110.5 millimeters. So knowing the location of the centroid for this cross-section, we can go ahead and calculate what our I is for the overall cross-section. So our I, that is going to be equal to, we'll do, switch the color. Oh, wait, I was the right color. The I prime for the top segment there. Plus its area times the square of its centroid relative to the centroid of the overall section. So 160 millimeters minus 110.5 millimeters, and then square that. And then we'll do this, and then the same thing for the contributions from the segments at the bottom. Got to keep in mind that there's two of those. So we'll take that and multiply it by 2. But the I prime component for each of those, 5,625,000 millimeters to the fourth, plus its area, 3,000 millimeters squared, times the difference between its centroid and the centroid of the overall section squared, 75 minus 110.5 millimeters squared. So, bust out the old calculator. So that gives us an I value of, let's see here, 2.95 times 10 to the 7 millimeters to the fourth. So let's just resketch what we're looking at here. So if we're trying to figure out what you know, the load based upon failure of these welds, well, then again we're given the stress, and we want to figure out what the maximum load is. But our stress equal to our V times our Q over IT. So if we're trying to solve for the maximum load, Vmax is going to be equal to stress max, shear stress max, times I times T all over Q. So the Q that we're going to be using there, yeah, it's just based upon this shaded section here, its area times the displacement between its centroid and the centroid of the overall section. So if the relative to down here, this here is 160, and this here is 110.5, which means that this distance here needs to be 160 minus 110.5, 49.5 millimeters. So that'll be the Y bar in our Q calculation. Also in that Q calculation is its area. So again, this distance here is 210 millimeters, and the thickness is 20 millimeters. Our T here, so again, that's the thickness of kind of where we're looking at. So if each of these is 20 millimeters, that means that the thickness that we're looking at is 40 millimeters. And then I, we just calculated already. So let's go ahead and plug everything in there. Our Vmax is equal to our tau max, which up here was given as 90 MPa, right there. So 90 MPa, I'm going to put that as newtons per millimeter squared, so we can start canceling some stuff out. 90 newtons per millimeter squared times our I, so that is 2.95 times 10 to the 7 millimeters. 95 times 10 to the 7 millimeters to the fourth, and then our thickness is 40 millimeters. All of this divided by our Q. So our Q, that's just the 215 millimeters times 20 millimeters times 49.5 millimeters. So we can start canceling some stuff out. So this millimeters squared here, that can cancel out 2 of these millimeters here on the millimeters to the fourth. So we've got millimeters squared times another millimeter, and then down below we've got all millimeters, so all those cancel out. We're left with newtons is the only unit here. So 90 newtons times 2.95 E7 times 40 divided by 215 divided by 20 divided by 49.5. That gives us a Vmax of equal to, let's see here, 4,098.943 newtons. Or guess what? We're going to say that is a Vmax of equal to You know what? Fuck it. I'm gonna round that to 500 kilonewtons. And yeah, that is that.